Hello everybody, welcome back to the Calculus Examination Preparation course. So we have been talking about the indefinite integrations in the previous lectures. So in today's lecture, we would like to talk about the definite integration and the methods. Okay, let's start.
Alright, so let's continue about the limit properties. We talked about the uniqueness property last time, and this time we're going to talk about the locally bounded property. So what is it? Well, the definition about this theory is, so if there's a limit, right, for the function f(x), so when x approaches to x0, f(x) approaches to a. So it means there's always exists and positive number n. So when you choose x in this range, from 0 to delta x, which means you're in the neighborhood of x0, right? Neighborhood of x0. And the range is about, 0 to delta x. So there's always, means the f(x) absolute value is smaller than n, which means, the f(x) is also bounded. Okay, let's look at this on the function graph here. Now we have, this function f(x). Okay, so it means if, we have a limit here, like this one is called a, okay? It's called a. Around, at the point x0. So it means if we choose the neighborhood of x0, right? Defined by the formula here. Okay, this is like x0 minus delta. This is like x0 plus delta. So in this region, now we have the f(x), in this region. So for example, we can say the f(x) equals to maybe 5 here and 7 here, right? So it means if n equals to 8 or anything which is a little bigger than 7, now we can say f(x) absolute value of it is smaller than 8. So it means, it is correct because, on this point it is 5, on this point is 7, and now on this point is even lower than 5. So we can say that the function's value is also, within a certain range. So we can say it is locally bounded. Yeah, locally bounded. Okay, so how can we prove this?
Alright, so here, let's do a little review here. So we have three things to change. We have to change the integration function f(x). So that's number one to change from f(x) to ft. We have to change the integration. Let's use another color maybe. Okay, so let's choose this color to indicate the first thing we need to change is, of course, the f(x) itself. And don't forget to change the corresponding integration variable from dx to dt. Okay? And then we have to change the integration range from the range about variable x to the range about the variable t. Well, because we have changed the integration variable from x to t, so we need to be careful to make sure that the integration range about t is the same with x. So we have to make sure that the phi t's prime, where the derivative is continuous. Okay, so it means on this range there's no breaking point. And also we have to make sure that the x equals to the phi t has to be within a range um, A and B inclusive. Yeah. Okay, we need an example to show us, okay, how we can use the substitution method to find out the definite integration, a number. Yes, a number. Okay, let's look at this. So we have integration range from 1 to 4, means x is from 1 to 4. And for this integration expression as 1 over the 1 plus square root of x. Okay, so this time, we see the square root operation on the denominator position again. So that's something we hate so much. We always want to get rid of it using different kinds of method, as long as we can think of. Okay, the same thing. So we want to refer to the substitution method this time to see if it works. So let's, have the square root of x as t, okay? So it means the x will become the t squared. Now this is the conversion back and forth. So it also means the dx can be write as 2t dt. Yeah, this step is about the initializing step. So it is very simple, and we have done this many times before. So now we have to consider something else, which is about integration range, the new one. Okay, but first of all, let's write down, let's just institute x with a t now. So we have the original integration expression converted to, okay, we will omit this integration range first, and we're gonna talk about it in just a moment. So we have something like here, no problem. What about a new range? Okay, we understand that t and x has a relation like this. So how about we just draw the function to show the relation between x and t? Okay, no problem. Let's draw this function graph here. So for example, this is x and this is t. So t equals to the square root of x. So we can simply draw it like this. No negative sides, right? Yes, because that's from the property of the square root operation. So we understand that if the original range is for x between 1 and 4, so the corresponding new range of t should be from 1 to 2. Yes, that's easy. So we can just put a 1 to 2 here. All right, let's continue. So the rest will be kind of easy. Okay, let's extract 2 outside of the integration. Okay, so we have this t over 1 over t and then dx. Yeah, we have this again. Remember, every time we have this, no matter it's t over the 1 plus t or t squared over the 1 plus t squared, as long as the numerator and the denominator are so similar, we can simply try to make them to be the same by just doing the equivalent transformation. So this time we can simply do the L1 and then plus 1, right, operation. Okay, so we're gonna have 1 minus 1 over 1 plus t dt. Okay, so now we can see that the next step is very clear. So the 1's integration will be t, okay? And then the integration for the 1 over t will be the line 1 plus t. Yeah, you can try it, right? We have been using this derivative of the line, blah, blah, for so many times. So, yeah, we can just write it in that way. Okay, so we have already done our integration, indefinite integration part. So now we need to put this feature of the definite integration, which is the integration range from 1 to 2. Okay, so for the t, okay, so let's try this one. We can say that, for t, we have 1 and 2, right? And we have this one from 1 and 2 again. T is very simple, so it's nothing but, 2 minus 1. It's very simple. But for this one, it's going to be just a little more complex. So we're going to have 3 minus, okay, the lion, 2. Okay, yeah, I'm sorry, I forgot the 2 here. Yeah. So let's try it. So we have 2 here, minus 2, lion 3, minus lion 2. Yeah, I think that's the final result. Alright, as you can see that, well, the definite integration, which is only a number, well, it's actually simpler in the final step. I mean, for the indefinite integration, we will have to put, this guy back finally, well, to find out the expression about x. However, for the definite integration, it's just a number, so we don't have to put it back in. So as you can see that, although the definite integration give us one more step to find out the new integration range, right? The new integration range, step 3 here. However, it will reduce another step, the final step, to put, the t equals to blah 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 x, the relations between t and x back into our final result about t, and to make it look the expression about x. So now you can relax. The definite integration is not that hard. Alrighty, so ready for the next challenge? Okay, so this one, because we're talking about all the examples about the definite integration, it does mean that we're going to use one specific integration method, but maybe more. So let's look at this example. Well, example 2. So we're not only will get a result for this example, but we also will find a very important formula. So the integration n. We have a subscript here. N means, okay, so for this equation from 0 to half pi, so we have the power for the sine, for the sine function, okay. We have the order as n, so that's why we use the subscript n here to indicate that. All right, so we have n as integer, okay, which is larger than 1. Well, it doesn't mean that n can never be 0. Later we can see that we're going to talk about that case. But usually, because if n becomes 0, it's going to be too simple. It's not going to be the integration about a trigonometry function. It would be just very simple, one's integration. So usually we say that, we want to make it look, meaningful. So that's what we say, n usually is larger than 1. Okay, let's see. So we have the in's integration like this. Okay, and from the previous discussions, whenever we see dx and maybe the cosine x or sin x before it, we can simply drag the sin x back into the dx position, right? To make it simpler. We can do the same thing here. So after we drag one of the sin x over, we're going to have only n minus 1's sin x left. So we're going to have, the minus cosine x here. Alrighty. Okay, so at this stage, I think a lot of students have already found out. Maybe we can try or consider the integration by part, just because we have this guy here, something here, and also we have this guy, which is so hard for you to integrate, right? So why don't we try the parts of the integration by parts, and also we can lower down the order here. Okay, let's try it. So let's have it as sine x to the power of n minus 1 and times the minus cosine x. So we're gonna find out the value because it is a definite integration. Okay, and then plus, still in the same integration range. Okay, so for this guy, so we have cosine x here. Okay, so we have the sine x to the power of n minus 1. So we're going to have sine x to the power of n minus 2. Yeah, because we took one order down. But here, because sine x, to the power of n minus 1 is a compound function, so that's why we have to consider. We have to, do the d sine x here, right? And of course, and then we're gonna have the cosine x here and dx, and we can further put the cosine x here. Okay, so let's write it down like this. Okay. Okay, so let's double check. So we have, n minus 1 here, so don't forget about that. So we can further put it down here. Okay, now it looks okay, good. Alrighty, so let's do the integration here. So we understand that if we have x as 0, so the sine x will become 0. So the this sine x to the power of n minus 1 times cosine x will become 0. Similarly, if we have x as pi over 2, the cosine x will become 0. So this whole thing will become 0 again. So that's why no matter what, the 2 points difference will become 0. This one will become 0. We don't have to talk about it. Okay, so let's just consider the next. Okay, so we have n minus 1 here. So only the integration range from 1 to half pi. So cosine x squared times the sine x to the power of n minus 2. Okay. Alright, so we want to further simplify the terms here. We want to make everything looks the same. So cosine x will be converted to x easily as, well, 1 minus sine x squared. Okay, so sine x to the power of n minus 1, minus 2, sorry about that. Okay, so for this whole thing, let's write it down as, okay, so this guy will be put into the parentheses. So the first term we're going to have is sin x to the power of n minus 2, okay, dx, okay, and the next term we're going to be the same within the same integration range, but about the sine x to the power of n, because we have the order 2 here and order the n minus 2 here, so they will add it together on a power part and will give us the final result as sine x to the power of n. Okay, so we have dx at the very end. Okay. Okay, so here we don't want to go further to use the integration by parts because we have already noticed something very interesting. So look at this part. Does it look similar to this one? But with the n replaced as n minus 2. So this one can be right as the notation given the statement of the problem as in minus 2, right? And what about the second item? Well, this one looks even close because it's exactly the expression of in, which is equals to such integration. So we can just write it down as in. Okay, so we want to find out what in will be because on the right side and on the left side of the equation, we all have in. So we can take it as a known variable and resolve this equation. But before that, we have to, distribute this n minus 1 to each item. Okay, here. All right, let's put, this one to the to the left side of the equation. So we're gonna have, 1 plus n minus 1 in equals to n minus 1 in minus 2. So we're going to cancel out this one and this one. So we're going to have in equals to n minus 1 over n and in minus 2. Alrighty, so by now we have found this. We have found this guy, and this guy, well, is the recursion formula. Okay, formula. Okay. Alright, so we have found out the recursion formula for this integration. So all we need to do next is to lower down the n. For example, if n equals to 20, right? So from this equation, we can find out a relation between I20, to I18. And then I18 will have a relation with I16. And later, we're gonna find, the relation, to the I0, right? This is when n is an even number. So, for example, if n equals to 19, so we're gonna find, the I19 related to I17, which is further related to I15, and further down, we're gonna have it related to I1. So the power of the recursion formula is as long as we can find, the very beginning, or to say the initial condition, like in our case, which is I0's value or the I1's value. Now we can, put, go back and find out, the I19's value or the I20's value or I18's value or I17's value. Yes, so we will find out any value you can imagine. Okay, so our job becomes to find out I0. Okay, let's try the I0. So from our, original function expression, we have, in equals to the integration between 2 and half pi, and to the, on the function sine x to the power of n. So let's use the n equals to 0's condition, okay? Okay, so sine 0x dx. So this is what we mentioned actually at the very beginning of the solution. So since to make this trigonometry function integration look meaningful, we have to make sure that n should be larger than 1. However, when n equals to 1, it actually can help us to do this integration. So that's why. So it's very simple. So it's just integration from 1 to half pi, but to the constant 1. So it's going to be x, okay, for the original function, and the difference between the 2 points on the original function is going to be half pi. Okay, so again, let's find out what the value should the I1 be. So we have this integration function here. So okay, so we have this. Okay, sorry. For the 2 pi, for cosine 2 pi is going to be 0, but for the cosine 0 it's going to be 1. So we're going to have 1 here. Alrighty, so I think we're almost ready. Okay, so let's get back to here. So we already found out what I0 is and what I1 is, which is about initial condition. So let's put it back. So if we have an even number, of course, this is larger than 0, of course. So we're gonna have the general formula for the INS. Okay, for the I will put it on the right maybe. So for the even number, so IN equals to n minus 1 over n for the I subscript n minus 2. And this can be further written down as I minus 3 and then n minus 2. The same thing. So blah, 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 blah. So finally we can have something like this. Because n is an even number. So when n minus 2, minus 4, minus 8, finally it's going to be 2 left, right? But on the top, because n is an even number, so when n minus 1, minus 3, minus 5, and all the way to the very end, we're going to have 1 left, okay? So this time, we for the very last, integration is going to be I0, right? Because when n equals to 2, this is what we have here. But when we do the let's see, the next operation, n minus 2, we're gonna have 0 left. But now we understand that I0 is nothing but pi over 2, right? Pi over 2. So you just have to do this multiplication for many times, and finally you just multiply the pi over 2 on the very end. You're going to find out the integration for the IN. Okay, but if n is an odd number, like n is 19, for example, right? We're going to do the same thing. So IN equals to the n minus 1 over n, and then times n minus 3 over n minus 2, and then all the way down to something like 2 over 3. Yes, and times I1. Okay, so I1 equals to 1 here. So we don't have to consider it anymore. It's just like this. Alrighty, so we have found out the general solution for the integration IN. So this is going to be very useful to help us to find out the integration for this series of integrations. So you can name it anyway. So since I found it, so I can call it it's like fence theory. Okay. Oh, sorry. Fence theory. You can also call it by your name, like James theory or janitor's Janus theory, whatever. Yeah, but we're gonna see how it can help us to find out the result. Okay. Let's see. So for example, we have I will call example 3. So let's see. If we have such integration here, right? So can you find out integration? Well, of course, the definite integration, which is a value or a number, quickly. Okay, try it. Yes. Okay. So from the theory, because we have a even number here, so we have 10. We have 9 over 10 times the 8 over 9 times 7 over 8 and blah 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 blah, all the way to okay, I will write everything down here. So we're gonna have made a mistake here, so this one should be, okay, 7 over 8, and this one should be 5 over 6, and should be 3 over 4, and 1 over 2, and finally, yes, because it is an even number, so we're going to have pi over 2. Okay, and if we have another, for example, we have this. So we're going to have 8 over 9, well, times 6 over 7, 4 over 5, 2 over 3, and yeah, then that's it. That's the end, 2 over 3, that's the end. Alrighty, let's look at another example about how to apply the comprehensive integration methods we have learned so far. As I told you, usually you can just put the methods for the indefinite integration to our definite integration, because I always have to find out the original function anyway, so it doesn't matter. Okay, so let's look at this one. So it's about integration from -1 to 1. Okay. Okay. So for the definite integration, we usually have to check out if it is an odd function or even function, which means if the function is ceramic like this, about a 0, or it's not. Okay, so this is the even function. So it is symmetric about the y-axis. Good. So if it is a odd function, we say that it's actually symmetric around this O point. Well, there are also some functions which is not even or odd function, maybe something like this. It does not matter. Yeah. Okay. So if it is an even function, for example, if we have a symmetric integration range, maybe from like this one, from -1 to 1, right? So we have this part and this part, and of course, the whole integration from -1 to 1 is nothing but the 2 times of the integration from integration from 1 to 0 to 1. And also, if it is a odd function, so we have integration maybe from -1 to 0 like this, and then we have the integration from 0 to 1 like this. So the absolute value of those two integrations will be the same, but with the opposite signals. So that's why we can say that integrations from -1 to 1 for the odd function will be 0. Yeah, so that's why we usually have to check if it is odd function or even function, which can help us to save a lot of time and energy, especially when we have the symmetric integration range. So in this case, well, the square x squared times the square root of 1 minus x squared is an even function. Well, you can try, maybe you can try the 1 and -1. And so the f1 equals to the f minus 1. You can try it. Yeah, so that's why it's an even function. So if we make sure that it's an even function, so we can further write it down to be 2 times of the integration from 0 to 1. So when x squared times the x minus 1 minus x squared. Okay, and also from the observation, we have this very familiar format appearing again, which is about, the a squared minus x squared, right? So every time we see this integration, we have to associate it with a substitution method on the trigonometry function side. Okay, so after this, now we can say let x equals to sine t. And of course, if we want to make sure that, well, the x is also, range is also from 0 to 1, we have to make sure that t is within a range 0 to pi over 2, right? Okay. Okay, so let's replace the original integration in 3 steps, okay? So the first one is to replace the integration expression. So we have x equals to sine t, so the x squared will be sine t squared, okay? And also here, we have 1 minus sine t squared, okay? And this, for the, the second step is to replace the dx to something like dt. So let's try it. So dx equals to cosine t dt. Good. Yeah, that's something we want to see, cosine t dt. Okay. And finally, we have to replace the integration with a new one, or to say upgraded. So originally, we have x within a range 0 to 1, and a new range will be 0 to pi over 2. Okay? All right, so let's try it. So now we have sine squared t. Okay, in the middle we have cosine t, and also we have cosine t again, so we're going to have cosine t squared and dt. Okay, so usually we want to make sure that all the formats will be the same or similar, so we can simply convert cosine squared t to the 1 minus sine squared t. Okay, so let's try it. We have this, and this one can be further written down like okay. So all right, yeah. So by this step, maybe most of you would laugh. Yes, now we have this classical, format appearing again, which is Bernoulli's theorem or your name's theorem. Okay, so seems like we have an even number case, right, for the n here. So we're gonna use this first line of formula. So let's try it. So this one is gonna be okay. Let's expand it to let it look more easier. Okay, yeah, and also because we said that it's an even function, so that's why we can simplify it by times the 2 at the very beginning of the integration. So here, just in case we forgot in the very end, we can just add the 2, multiply the 2 here, yeah. All right, so the first one will become 2, okay, and times the 1 over 2 times pi over 2, because it's an even number. And this one's going to be 2 times the, so 3 over 4 times 1 over 2, and then pi over 2. What we're going to have is, so this one is going to be pi over 2 again. And this one is going to be this. And finally, we're going to have 1 over 8, or 1/8 pi. Yep. So that's the final answer. And you can see the power of the theorem we got from the example 2. If not, well, this is going to take you like forever to find out what the integration is. Because here we have, x, the sine t squared here. So you have to do more things if you just want to reduce the order here, and also here too. It's going to be very, very painful. All right, thanks to the theory we found out, it can save us a lot in many, many problems you're going to meet in examination. Alrighty, so that's the end of the definite integration. So hopefully you can review all the things we have talked about, the indefinite integration and definite version 1, 2, and hopefully we can get everything ready for the new steps. Alrighty, so that's all we have to know for the fundamental calculus. So if you're in a major such as the biology, biochemistry stuff, or the dental major or the medical major, probably you don't have to continue learning, and that's all you need to know. And even for the majors, which requires much more mathematics, such as the physics or the economics or the calculation, finance major. So with a basic fundamental calculus knowledge, you can probably pass your examination already, which means you can get a C or D if you have mastered all the knowledges we have covered in this course. So if your major requires more mathematics, such as you're gonna do the calculation, chemistry, or to say the quantum mechanism or the electrical engineering, so it is recommended that for you to continue learning the calculus. So in the intermediate calculus course we're gonna have, we will introduce more calculus knowledges, such as the multivariable calculus and also the differential equation and much more. And also, not only will introduce more knowledges, but also we will deepen the knowledge we have learned, such as the implementation of the one variable differentiation. Since we introduced the basic calculation about the derivative, but we haven't got too far about its application. But in the intermediate course, we're going to show more, such as how to, like find out maybe the maximum, minimum or maximum, or the local minimum or maximum, and the whole minimum or maximum, and much more. So if your major requires this, well, please continue. So and join me in learning the calculus and having fun in the advanced mathematics.